Hello viewers, today we are going to discuss about transient response of second order circuits. The basics of transient analysis has been discussed previously in another video. You can go through that video first by clicking on the I button above. In that video, I have discussed transient analysis of first order circuits, taking example of RC circuit. So today I am going to take a series RLC circuit, which is typically a second order circuit with three passive elements, namely R, L and C. The series RLC circuit is called a second order circuit as any voltage or current, that is, response of the circuit, can be described by a second order differential equation for the circuit analysis. This is also evident from the fact that if I take KVL around the loop, we will get this equation, and by substituting the value for loop current, which is also equal to the current flowing through L and C, and rearranging the terms, we will get a differential equation of second order. Also, a second order circuit may have two storage elements of different types or the same type, provided elements of the same type cannot be represented by an equivalent single element. RLC circuit have many applications in electronics. Because of their resonance qualities, they can be used in many different types of oscillator circuits. They can be also used to select a very specific range of frequencies from a much broader spectrum. Radios and televisions with analog tuners typically use an RLC circuit to tune in a specific frequency or channel. RLC circuits are also used as band pass filters, band stop filters, low pass filters or high pass filters. Tuning a radio signal is an example of band pass filtering. So, the application of RLC circuits are numerous. Let's come back to the series RLC circuit. The characteristic equation modeling the circuit is given by this equation. This quadratic equation is known as characteristic equation since the roots of this equation dictates the character or behavior of the circuit's response. Here, alpha is the damping factor, which is a function of resistor R. Damping is the gradual loss of the stored energy, which can be seen as continuous decrease in the amplitude of the response, and this damping effect is due to the presence of resistor R. Omega naught represents resonant frequency, which is given by 1 by root over L into C. Depending on the values of damping factor and resonant frequency, we have three different types of responses. When alpha is less than omega naught, we get underdamped response. In terms of circuit's components, it can be expressed as C less than 4L by R square. In this case, the complete solution is given by the sum of transient response and steady state response, where WD is the damped frequency of oscillation. Likewise, when alpha is equal to omega naught, the response is critically damped, and when alpha is greater than omega naught, the response is overdamped. The corresponding equation for complete response is as shown. Now, to find the values of these constants A1 and A2, we will take the help of the initial conditions for the circuit variables and their derivatives. Let us discuss the step response of series RLC circuit for three different resistor values. When R is equal to 40 ohm, we get a underdamped response. Like transient response for first order, we start our analysis by finding the initial conditions, that is, analyzing the circuit for t less than 0. For t less than 0, ut equal to 0. The capacitors behaves like an open circuit, while inductor acts like a short circuit. So we will get 0 initial responses both for voltage across the capacitor and current through the inductor respectively. We will make use of total response equation for underdamped response to find the voltage across the capacitor. By making use of the initial conditions and their derivative, the constants A1 and A2 can be obtained. So, this is the final equation obtained for R equal to 40 ohm. Value of the response for some definite time has been found so that later the graph obtained by simulation using Multisim could be verified. A very similar analysis can be carried by taking resistor value to 200 ohm. In this case, as the damping factor is equal to resonant frequency, so a critically damped response will be obtained. By substituting the values for the constants, we will get this equation as the total response for the circuit. When R is increased to 1 kilo ohm, a overdamped response is seen. Likewise, this is the response for overdamped case. This is the Multisim software interface. Let's start our simulation with R equal to 40 ohm, which is our underdamped case. Before proceeding further, let me show you how I have set the values for step voltage. Double click on it. Under the value tab, I have set the final level of the step to be 5 volt. Rise or fall time as low as possible and rest 0. To start the analysis, go to Simulate, Analysis and Simulation. Select the type of analysis as Transient. Under Initial Condition tab, select Set to 0. Since for our case we have 0 initial conditions, let me set the duration of transient analysis to 5 milliseconds. To get the output smoother, I will set the maximum time step to 10 to the power minus 6 seconds. Under Output tab, select V4, which represents the voltage across the capacitor. Click on Add and run the simulation. Let me set a lighter background by clicking on this tab. Click on the Grid tab so that the coordinate points are easily readable. Let me bring the cursor and verify this graph with our theoretically obtained voltage equation for some of the calculated coordinate points. So, a ringing response or a damped oscillation is exhibited by the underdamped response. As you can see, the initial value of the response is 0 and finally it settles down to 5 volt, which is equal to the step input voltage. Now let us verify the graph at t equals to 1 milliseconds and t equals to 2 milliseconds respectively. If you set the cursor to 1 millisecond, you can see the corresponding value of Vt is 5.68 volt, and when t equals to 2 millisecond, Vt is equal to 4.9 volt. So it matches with our theoretical result. Now let us come to the second case where R is equal to 200 ohm, which is our critical response case. If I run the simulation, we'll get this graph. So you can see this graph has no ringing effect and it settles down to its final value very rapidly. Let us see the overdamped case when R is equal to 1 kilo ohm. Now if I run the simulation, you can see the graph takes relatively a longer time to reach its final value. So if you want to view the three graphs together, then you can go to Graph tab and can add all the previous graph one by one. You can also change the title of the page by double clicking on it. Let me rename it as Step Response of Series RLC Circuit and press OK. Thus, we have analyzed the series RLC circuit for three different cases, namely underdamped response, critically damped response, and overdamped response, respectively. So that's all for today. If you like this video, give a thumbs up and don't forget to hit the subscribe button. Thank you.